Bismillahirrahmanirrahim. Welcome back. Today, in this video, we will show the implementation of multiplexer or mux in Verilog HDL using different ways. So, multiplexer we have discussed in the last video in very detail how it works and what are the working. So these different ways, basically in this video we will only discuss three: the gate level implementation, logic statement implementation, and case statement implementation. All these have some things in common and something different. The first one is gate level implementation. So we will start from here. Method 1, gate level implementation. So in DLD, this type of representation, a circuit is specified by its logic gate and their interconnections. What are interconnections? We will see in code. This is actually the same code that we already discussed for the operators, but there is some difference in the syntax or some parts of the code. This first one is obviously the same. This on input output declaration or name, output, input, and wire. This is basically the interconnection we were talking about. This not control and not control 2 and other wires. These are basically the interconnections, and these are the gates. They are declared in specific way. These are the inputs, and these other are the lines. This not gate, this is the input line basically, and the other one is its input control line 1. So all are implemented in the same way. Let's have an overview of the multiplexer that we had in the previous video, and the link to that video will be in the description. How a multiplexer actually works will be shown in this circuit. This is a 4-to-1 multiplexer, and let's simulate it and see that how these selection lines control the working of these gates simultaneously. So in a multiplexer like this, there are 4 inputs, and one of these 4 will be displayed here in output. So these selection lines are basically the selectors from these 4, that one will be displayed in output. So if we give it a 0 0, and this gives the gate 1 permission to display its output in the to display its input in the output. If we change this selection lines, then this will not allow it, the first one. If we give it a 0 1, this allows the second gate to display its output. If we give it a 1 0, then it allows the third gate. If it is 1 1, that it allows the fourth gate. So it was basically an overview of the multiplexer, and this will implement it in the same way in the Inquartus. Let's make a new project and implement this code in Inquartus. I have already made a directory on desktop for lab 6, so we will save it here in lab 6 directory. Name it method 1. You can name it as you wish but it should not be a built-in function name or a variable name. Back to the simple code. We see that these are the input and output, inputs and outputs. Let's see what are these selection lines and these 4 inputs and 1 output. Basically we have divided into them. We can say line by line code here in module that I already said that this is same always. This is also same in other methods except for the wires. And the part 3 is basically the this is the basically the unique thing in this method, that we are declaring the gates and their input lines and their inputs. This is the input. So back to the quartus, we will make a new variable verilog hdl file. We should copy the same code into quartus. Let's change the name to the name of our project, method 1. All other code is obviously same. This is the syntax that is different from others, the gate implementation. Let's compile it and give it some time to compile, and we will back. So since it's compiled successfully, we will now see that how it implements the gates. We will go to RTL viewer, let it compile and load schematic. So this is the schematic, the gate implementation. These are the two control lines. These are the 4 inputs and 1 output. So more or less it is same as we have saw in the protease, and this confirms our code. And now we will see how it behaves in waveform simulation. So the method is same. We will load nodes here and we will give it some input. Now this input actually depends on how generally mux behaves, so we can confirm its behavior. So let's see that when we give the selection line 0 0, okay, so the first gate's input is displayed in the output. Now come here in the simulation. If we give control line 0 0 and the input of 1 is input 1 is high, okay, so we predict that this output should be a high, so that this input is displayed in this output. So let's run this simulation. It will take a bit. Our simulation is ready, and it confirms that the high of input 1 is displayed at the output high. That's it for this method 1. We saw the code, how it is different from other methods. We will discuss in the future that these gates are declared, and these interconnections are declared, and the behavior is same. Let's see one more example. If we give it a 1 0, so I think 1 0 will allow the third gate to be displayed in the output. So if we see that we give it 1 0 in the selection lines, sorry, if we give it 1 0 in the selection lines, and this is all others are low, and the third gate is high, then the output must be high. This will confirm that these selection lines have allowed the input 3 to be displayed in the output. we can displayed in the output. And let's cross check it, that if we give input 3 a low, if we give input 3 a low and keep the same selection lines 1 0, and we give input 2 a high, then it must not give a high in the output, because it will not allow the input 1 high on the output, and the input 3 will be displayed in the output, which is low. So this must be low. That confirms our mux concept, and that is it for now. So the next method is logic statement implementation. In DLD, we know it as data flow modeling of combination logics. This is basically this method uses the operators that act on operands, 2 operands or 3 operands, to produce a desired result. What does that mean? We can understand it from a code. The first two, 3 lines are same for all. Sorry. The input output declaration, uh, the output input. This is basically the special line for this method. This is a statement. It is a logic statement which uses operators between different inputs to give a particular output, and the output is same. uh, we will see in the we already discussed the mux in protease, and how it gives an output. The selection lines decide the output by allowing only one at a time. So this code will um, implement, this whole statement will implement the operation of a mux. We divide it in two parts. One is the one that is same for all, this declaration of input output, and these are the inputs. And part 2 is this is part 2, sorry, this is a statement in which operators are used to give a desired output. Now let's go to Quartus. You can copy the code from here, go to Quartus, make a new Verilog HTML file, change it to the our project name. all the thing is same. We have this statement. This is called as logic statement, and this is basically the special thing in this method too. We will see its implementation in RTL viewer. Sorry, let's compile it first, and it will take some time, so we will stop the recording. So we are done with compilation, and similarly we'll first see RTL viewer. Does it implement the gates in the same way or not? Yes, in the same way as it was in the previous method, although the sequence is different, but it exactly implements the same as we see here. Now we will simulate its gates in waveform from node finder. We'll see. Now previously we have given it the control lines to the inputs to control lines as 0 0, and we confirmed that if we give it 0 0, then it displays the input 1 on the output. because if we give it a high, it displays high in the output. If we give it a low, it displays low at the output. And if the control lines are 0 0, and we give control line sorry, input 3 a high and input 1 a low, then it gives a low output. This confirms that whenever the control lines are 0 0, it will only allow the gate 1 to display its input on the output. Okay, that is a short theory of what will happen. So previously we have shown 0 0 and 1 0. Let's now see 0 1. Okay, which will allow input 1 to be displayed at the output. So sorry, input 2 to be displayed in the output. So we will give it a high. Okay, let's let's do it in a different way. If we give all the inputs a high, okay, this will confirm our result. If we give in all the inputs are high, and we will see that what it uh, gives in its output. We predict that it will give a high in the output. It gives a high in the output. Now let's see, if we give input to a high, if we give input to a low, then the output must be a low. So it will confirm that it doesn't allow any other gates to change our output. So let's give it a low. Sorry, let's give it a low. Okay, and see what happens. Sorry, no, this is input 1. Let's give it a low. So 0. Okay, let's see. Exactly. Look, the input 1 is low, then output is also a low. So that confirms our result. That's it. Now the third method is case statement implementation. In DLD, case statement is basically the one which represent digital circuit at functional and algorithmic level. What does that mean? We will see in the coming video. It is used mostly to describe sequential circuits, but we will use it for combinational circuit. We can do that. The code is the first part of the code is same for all this module and output input. Now we will see what all this thing is. Remember that whenever this always statement will come, this is basically a statement. And what is case? These are the 4 cases. So in this method we declare a variable. In this it is a reg out. Okay, we declare a variable and we assign different values to this variable on the basis of how it will how it will be compared with the case variables. So case variables are if it is a 2-bit case, and if both control line 1 control line 2 are 0, then this input variable will be assigned to output. The value in input, if whether it is a high or low, it will be assigned to out. Okay, and if it is a combination of 0 1, then it will the input to variable into variable will be assigned to out, and same as other. Now we say that none of these inputs are there, or none of these control lines are given uh, to the input. Then there comes a default case, and it will display that please check control bits, these control bits, that none of them, if none of them are selected, then we cannot assign any of these four to out. Okay, let's divide it into three parts. Actually, this reg out is in part 2, so this is same for all. Reg out and this statement is in part 2. We say that these are always come together, reg out and always statement, and these are the case statements which in which there are four cases and a default. It is not necessary that there are four cases, that depends on the code or the gate implementation we are doing. Then but in mux there are only four cases, whether the in 4 to 1 mux there are four cases, whether the control lines are 0 0 0 1 1 0 or 1 1, like that we have seen previously. Whether it is 0 0, it is 0 1 1 0 or 1 1. Okay, let's end this. Last thing is end case. This will come after we have completed our cases and default statement. Now come to Quartus. We will create a new file of verilog HDL. Let's copy the code from the manual, method 2, case statement. These are the cases, default and module in case. Let's compile, and it will take some time, so we will stop the recording for that. We have successfully compiled our code. Let's see in article viewer the gate implementation, and here we see selection 1 to 0. Let's see the code. We are given with 4 inputs and cases. So this is a different different way of implementing the same code. Sorry. It is the same as this one, but in a different different shape. Let's confirm it from our waveform simulation. And we will confirm it very easily. How? If we say from the code, we say if these two are 0 0, then it should assign input 1 to output. Let's see it does that or not. So let's give it a high. We can give it a low, but it will not differentiate it because all others are low and this is a high. So there should be a high in the output if it confirms it well. Look, it confirms our result. So we need not to go to other things, but let's do one more step to confirm it. Let's give all of them a 0 and this high, this one a high, and this one a high, the fourth one, so that when both of the control lines are high, then it should assign the input 4 to the out. So there must be a high due to this input 4. We confirm it again that that this code is implementing a 4 to 1 mux, but we have saw 3 different methods of implementing the same thing. That is it for the 3 methods. Now we will move to different examples in the further video.